Good day, everyone. My name is Mahammad Dadashov, and today I will be presenting the outcomes of my internship project, titled Analysis of my internship project, titled Analysis and Mathematical Modeling of Telemetry Performance in UAVs under Electronic Warfare Conditions. This work was conducted under the supervision of Mr. Mukhtar Azizullayev and Dr. Eric Christoffel at the National Aerospace Agency. Over the course of the 2 months, I explored how UAV's telemetry system behave when exposed to jamming and interference, and develop mathematical models to predict their performance. Now, let start by explaining the context. UAVs or unnamed aerial vehicles rely heavily on telemetry systems to transmit critical data such as GPS position, attitude, system health, and mission parameters to ground control stations in real time. In modern conflicts or even crowded signal environments, these telemetry links are vulnerable to electronic warfare or EV, which can include deliberate jamming or signal interference. This raises a serious operational risk, and distributed telemetry can lead to loss of the control, mission failure, or even complete UAV loss. The real goal of my project was to simulate such scenario using low-cost NRF transceivers and analyze how the telemetry performance degrees under different jamming conditions. I focused on three core metrics: signal to noise, bit error, and packet loss. I also used free space path loss or FSPL modeling to predict signal behavior over distance. Now let's move to methodology. I designed a point-to-point telemetry tested using NRF models and Arduino Uno boards. These were set up to transmit, receive packets in an indoor range of up to 10 meters. I simulate two scenarios, one with clean signal conditions and one with jamming interface. To simulate electronic warfare, I introduced jamming via a secondary NRF module transmission on the same frequency band. Package data was logged using a custom C# desktop application, and also proceed in Python using pandas and other libraries. In terms of modeling, I applied the FSPL equation to predict signal attenuation over distance. Use the standard SNR formulas to assess signal clarity and estimate BER using the Q function, particularly for binary phase shift keying modulation, which is relevant for NRF models. Overall, this setup provided both theoretical and practical insights into telemetry behavior under EVE stress. Now, in this slide, I present key findings. We observed that one SNR dropped below 10 decibel, package loss exceed 70%. This effectively makes telemetry unreliable for mission critical applications. The communication completely failed when jamming power spreads about 6 decibel above the signal, meaning even mild interference could cause full signal collapse. Importantly, the empirical results shows strong correlation with the SPL and BER predicts with a calibration error of just 0.03. This small deviation confirms that the mathematical models used are reliable for estimating performance under jamming conditions. These findings help define thresholds behind which communicate fails, which is critical for UAV design and planning. Now uh, we have discussion slide. So, what does mean in practical terms? Firstly, uh, the NRF module also cost efficient provides to be highly vulnerable to interference. It's suitable for basic telemetry tasks but cannot be relied upon in hostile environments. Secondly, jamming powers is clearly the most influential variable in determining reliable. As soon as the interference level crosses a certain point, the system performance drops sharply. These results align with prior uh, studies from Sklar, uh, Goldsmith, and other professors on wireless signal degradation under stress, confirming the validity of our approach. From an engineering perspective, I recommend that future UAVs design incorporate stronger RF modules, frequency hopping protocols like FHSS, redundancy via dual channels, and error correction technique to attain reliability under EV. Now we have to summarize, UV telemetry systems are extremely sensitive to electronic warfare. Even modest interference as low as 6 dB decibel above the base signal can cripple communication. Fortunately, our mathematical models, especially FSPL and SNR based, will accurately predicted this degradation and can therefore be used to assess risk and inform design. The critical threshold we defined allows engineers to define safe operation distance and signal margins for UAV telemetry. Going forward, implementing adaptive modulation and anti-jamming protocols will be essential for any UAV system intent for use in contested environments. This internship also helped me deepen my technical knowledge in embedded system, wireless communication, and telemetry signal modeling, all of which I plan to build on my in future academic and professional work. Uh, Now, these are some of the core references that support my modeling and simulation work. I relied on foundational texts by Goldsmith on wireless communication, Sklar's work on digital communications, and several IEEE publications like those by Nemenami and Zuhu, which focus on especially on UAV telemetry under interference. Their theoretical models and experimental frameworks help me both design and validate my own tests scenarios. Now, this work is possible through resource and mentorship of National Aerospace Agency, where I've hosted for this internship. I would like express my sincere thanks to engineers, technicians, and academics at the US Telemetry Lab, as well as to UFAS and ADNSU for their continuing academic support. Thank you all for attention. I would be happy to take any questions you might have regarding this model, test methods, or broader implication of this work.